Welcome to the General Chemistry 2 class. This section is on chemical kinetics. This lesson is about the zero, first, and second order reactions. Let's begin. In this lesson, we will differentiate zero, first, and second order reactions. A differential rate law is an equation that relates the rate to the concentration of the reactant. It is the form of rate law discussed in the previous lesson. An integrated rate law shows the concentration of the reactant remaining at a given time. It is derived from a differential rate law that is simplified by employing techniques in calculus. Reactions are governed by a certain rate law. Performing kinetic experiments give us data that help us determine the order with respect to each reactant. In turn, the rate law for the reaction can be deduced. Some classifications of reactions based on the order of reactions include zero order, first order, and second order reactions. In the discussion, we will limit the discussion to reactions with only one reactant. Consider the following reaction, A yielding products. A zero-order reaction has the following differential rate law. Rate equals K times the concentration of a raised to 0 or K, simply K. The equation implies that the rate does not vary with reactant concentration. For zero-order reaction, the corresponding integrated rate law is given by concentration of A at any time equals initial concentration of A minus KT. The unit for K is concentration per unit time. For example, mole per liter second. A first-order reaction has the following differential rate law. Rate equals K times molar concentration of A. Looking at the equation, doubling the concentration of the reactant doubles the rate of reaction. The corresponding integrated rate law for a first-order rate law is given by concentration of A at any time. T equals initial concentration of A times e raised to the exponent negative KT. The unit for K is inverse time. For example, inverse second. A second-order reaction has the following differential rate law. Rate equals K times molar concentration of A squared. The equation suggests that doubling the concentration of the reactant increases the rate of reaction by a factor of 4. The corresponding integrated rate law is given by 1 over concentration of A at any time. T equals 1 over initial concentration of a plus KT. The unit for K is inverse concentration times inverse time. For example, liter per mole second. To summarize, reactions are governed by a certain rate law. Some classifications based on the order include zero, first, and second order reactions. That would be all. Thank you. Welcome to the General Chemistry 2 class. This quiz is about zero, first, and second order reactions. Let's begin. Identify the order of reaction as described. In the differential rate law, the reactant concentration is raised to the exponent 1. Identify the order of reaction as described. The rate does not vary with reactant concentration. Identify the order of reaction as described. The integrated rate law is given by concentration of capital A equals initial concentration of capital A minus Kt. Identify the order of reaction as described. Increasing the concentration by a factor of 3 increases the rate of reaction by a factor of 9. Identify the order of reaction as described. The integrated rate law is given by concentration of capital A equals initial concentration of capital A times e raised to the exponent negative Kt. Identify the order of reactions as described. A unit of the rate constant is liter per mole second. Identify the order of reaction as described. The integrated rate law is given by 1 over the concentration of capital A equals 1 over the initial concentration of A plus Kt. Identify the order of reaction as described. A unit of rate constant is inverse second. Identify the order of reaction as described. Increasing the reactant concentration by a factor 10 increases the rate of reaction by a factor of 10. Identify the order of reaction as described. A unit of the rate constant is mole per liter second. That would be all. Thank you.